Hello, and welcome to my YouTube channel called Statistics from A to Z, Confusing Concepts Clarified. These videos are based on content from my book of the same name, which is published by Wiley. For more information on the book and these videos, please visit statisticsfromatoz.com. This video is the sixth in a playlist on regression. 3 of these videos are identified with the arrowhead type of bullet. Simple linear regression, multiple linear regression, which is the subject of this video, and simple nonlinear regression. Those are the 3 types of regression analysis covered in the book and these videos. A 4th type, multiple nonlinear, is beyond the scope of this book and these videos. See statisticsfromatoz.com/videos for the latest status of my videos. As usual in the book and in these videos, we'll go quickly through a list of keys to understanding, or KTUs, to give you the overall picture on one page. And then we'll go into detailed explanations of each of the keys. For this video, there are 5 KTUs. The first key tells us that the same basic principles that apply to simple linear regression and to residuals also apply to linear regression, which uses 2 or more variables, that is, to multiple linear regression. However, additional considerations and complications apply, and here is the form of the equation for the regression model. The second KTU states, start by identifying possible predictor variables, that is the x's, using subject matter knowledge. Then collect the data, then plot the data, and perform correlation analyses to identify candidate x's for the regression model. The third key says, the more is not the merrier. Drop x variables which are not correlated with the y variable or which are correlated with other x variables. The fourth key says, from a data set of y and corresponding x variables, statistical software can provide the regression model and a number of statistics for evaluating it. The fifth and final key to understanding says, a model cannot be validated with the data used to produce it. Use design of experiments to design and conduct controlled experiments on the predictions from the model. And here on one page are the 5 keys to understanding the concept of multiple linear regression. You may wish to pause the video at this time to read them all together. Okay, let's take a closer look at each of the keys to understanding. Key to understanding number 1 starts out by saying, the same basic principles that apply to simple linear regression and to residuals also apply to regression with 2 or more x variables, which is multiple linear regression. For simple linear regression, there is only one x variable, that is only one independent or predictor variable. The equation for the regression model is y equals bx plus a. This is the equation for a line in 2-dimensional space, like on a sheet of paper or on a computer screen. For multiple linear regression, we can have multiple x variables, and the equation looks like the one shown above. And this is for a straight line in multiple dimensions. The model can exist in 3, 4, or more dimensions. This, of course, would not be possible to graph on a sheet of paper or on a screen. The KTU goes on to say that additional considerations and complications apply. For one, there are several methods and measures for selecting the x variables. Also, the coefficient of determination, r squared, tends to grow solely as a result of increasing the number of x variables. However, there are other statistics which don't have that shortcoming. You can't plot a 2-dimensional graph with 2 or more x variables. With 2 x variables plus 1 y variable, the regression produces a best fit 2-dimensional plane in a 3-dimensional space. Beyond that, we get into an imaginary realm of 4+ dimensions. However, we can and do use separate individual plots of y plotted against each individual x, as we'll soon see. Usually there are a number of candidates for inclusion as x variables in the regression model. Various methods and statistics are employed to winnow these down to a best subset or subsets. And ANOVA is often used to help evaluate the model. And there may be interactions between or among the x variables. Key to understanding number 2 says, start by identifying possible predictor variables, the x's, using subject matter knowledge. Then collect the data, then plot the data and perform correlation analyses to identify candidates for the regression model. We'll go through this step by step. Step 1, the first thing to be done does not involve statistics. Use your subject matter knowledge and that of other subject matter experts if available to identify all measurable causes, x variables, of variation in the y variable. It is important to get this right because once the data are collected, you can't go back and get additional data on additional x's. Step 2, next collect the data. For each subject, you must collect all the x values at the same time. You can't record someone's blood pressure today and then come back a month later to get their weight. This is why step 1 is so important. Here's an example. We are developing a model for predicting house price. House price is the outcome variable, the y variable. In step 1, we involved real estate assessors as subject matter experts. They identified 4 possible x's. Actually, there are more, but let's keep this example simple. These are our 4 predictor variables. House size in thousands of square feet, lot size also in thousands of square feet, the number of bedrooms, and the number of bathrooms. Then in step 2, we collected the data. To keep this simple, we are just showing data for 7 houses. The y values are the prices in thousands of dollars as shown in the leftmost column. The 4 x values for each house are shown in the remaining 4 columns. Note that we must collect all the data at roughly the same time. If we collected data for 4 of the houses and then waited a couple of months to get to the other 3, market prices, which are the y values, may have gone up or down. And maybe not so much for this example, the relative influences of the x variables may change over time. So the leftmost column is the y value for each of our 7 houses, and the other columns are the x's. KTU number 2 goes on to say, then plot the data and perform correlation analyses to identify candidates for the regression model. Correlation analysis is described in detail in the second video in this playlist titled Correlation Part 2, the Correlation Coefficient. That video also explains the importance of plotting the data. That is because the correlation coefficient alone can be misleading in some cases. Here we have plotted the prices as the y variable, and there is one plot for y versus each of the 4 x variables. The x variables are the number of bedrooms, the number of bathrooms, the house size, and the lot size. KTU number 3 starts out by saying, the more is not the merrier. Drop x variables which are not correlated with the y variable, or which are correlated with other x variables. Simpler, that is fewer, x variables is better. It can be a bad idea to include a large number of possible x's. This is due to potential interactions among the x variables. It can also result in increased expense for gathering data. For each possible x, we do a scatter plot of y versus the x. If the scatter plot shows a roughly linear correlation, proceed to step 4. Otherwise, drop that x variable from consideration. Here, the scatter plots show a roughly linear correlation for 3 of our x variables, the number of bedrooms, the number of bathrooms, and the house size. and our calculations for the correlation coefficient R support that. However, the lot size does not show a linear correlation, so we will drop that variable from our model. The second part of KTU number 3 tells us to drop x variables which are correlated with other x variables. So we need to calculate the correlation coefficient R between every combination of pairs of our remaining 3x variables. Excuse me. And if any two x variables are strongly correlated, we need to drop one of them. R greater than 0.6 or 0.7 or more seems to be a commonly used clip level for strongly correlated. In our example, R equals 0.57 for house size versus bedrooms, 0.46 for house size versus bathrooms, and 0.42 for bedrooms versus bathrooms. All of these are below the 0.6 clip level for being strongly correlated, so we'll keep these three remaining x's in our model. These three remaining x variables are house size, bedrooms, and bathrooms. Key to understanding number 4 starts out by saying, from a data set of y and corresponding x variables, statistical software can provide the regression model. In our example, the software provided this equation for a regression model. Y equals negative 34.75 minus the quantity 5.349 times house size plus the quantity 85.506 times bedrooms plus the quantity 77.486 times the number of bathrooms. Negative 34.75 is the intercept, and the three coefficients corresponding to the three x variables are negative 5.439, 85.506, and 77.486. Key to understanding number 4 goes on to say that the software also provides a number of statistics for evaluating the model. Our software also produced 3 tables of statistics. Here are the first 2. R-square tells us that 97% of the variation in the value of the house price is explained by the model. The adjusted R-square number is almost as good. So this model is a very good fit for the data. The standard error is the standard deviation of the errors, which are the residuals. The ANOVA section evaluates the null hypothesis, which says that the regression model explains none of the variation in the data. ANOVA calculated a p-value of 0.001. With some software, p-value is labeled significance f. P is the probability that the results obtained are a false positive. That is, the probability that the model is not valid. Here the p-value is well below the usual clip level for alpha of 0.05, so this is further corroboration of the validity of the model. The third table in the output from the statistical software looks at properties of the individual components of the model. It will tell us which of the 3 x variables we selected make a statistically significant contribution to the model. Those will be included in the final version of the model. The coefficients for the 3 x variables in the regression model, house size, bedrooms, and bathrooms, are shown in the second column of this table. P-value. The software also calculated p-values of each of the 3 x variables. We can compare the p-values to a pre-selected value for alpha. Most commonly, alpha equals 0.05 is selected. If the p-value is less than 0.05 for a given x variable, then we can conclude that the coefficient of that x variable is different from 0 to a statistically significant degree, and thus it can be included in the model. We see that the p-values for bedrooms and bathrooms are comfortably below alpha equals 0.05. This tells us that they do make a statistically significant contribution to the model. So we will retain them going forward. However, for house size, the p-value is very large, indicating that we should not include it in the model. The statistical software can identify a best subset or best subsets of x variables. There are a number of methods for selecting best subsets. The best approach may be to select a set or sets of x variables which optimize one of these three statistics: R squared, adjusted R squared, or Mellow's CP. R squared, or otherwise called R squared, is the square of multiple R in multiple regression. As discussed in part 2, R squared is the proportion of the variation in Y that is explained by the model. Being a proportion, R squared ranges from 0 to 1. The larger the value of R squared, the better. The drawback to R squared is that it tends to get larger simply as a result of more x variables being added. This is another reason why the more is not the merrier. R squared equals SSR divided by SST, which equals 1 minus SSE divided by SST. Adjusted R squared adjusts for the shortcoming in R squared. If n is the sample size and p is the number of predictor x variables, then here's the formula for adjusted R squared. Now, there are mixed opinions regarding whether it is a substantial improvement over R squared. Mellow's CP makes a similar adjustment. It is preferred by some experts, but it is not often included in the standard output of software and spreadsheets. If we decide to use R squared, we see that the top two options have the same value, negative 0.970. Remember from KTU number 3 that the more is not the merrier. So a regression model with 2 x variables is preferable to a model with 3. And we can use just 2 x variables, bedrooms and bathrooms, in our model. And for the best subset bedrooms and bathrooms model above, the regression model is y equals negative 38.824 plus the quantity 83.725 times the number of bathrooms plus the quantity 76.078 times the number of bathrooms. What we just did was to test the model with the data that produced it. That was useful in determining the best subset of x variables to include in the model and to give us confidence that we are on the right track. But we're not done yet. First, as noted in the part 3 video, we must test the residuals. Then the whole purpose of regression is to make predictions about data we have not yet collected. So we must conduct experiments in which, for specific values or levels of each of our x variables, we predict a y value. There is a discipline called Design of Experiments, DOE, which describes how to do this in order to get statistically significant results. This needs to be done before we can make any definitive conclusions about cause and effect between the x and y variables. In the book, there are 3 articles on design of experiments, so I'll probably do 3 videos on the subject. In this video, we have referred to 5 previous videos in the playlist, and on this side, you can also see the next videos which are planned at this point. The one listed last, ANOVA versus regression, was completed a while ago as part of the playlist on ANOVA. For the latest status of my videos, please see the videos page of the book's website. Okay, that concludes our clarification of the concept of multiple linear regression. If you liked this video, please remember to press the thumbs up like button on your screen below. I'll be making more videos of some or most of the 60+ concept in the book if folks like you tell me more videos are wanted. Please subscribe to this channel to be notified when new videos are uploaded. Also, the website statisticsfromatoz.com has a listing of available and planned videos. Now, videos like this one can be very helpful, but they're not very handy when you want to quickly look up something on the job, while studying, or during an open book exam. For that, nothing beats a book or an ebook. You can also learn more about those on the website. I'd recommend following my blog at statisticsfromatoz.com/blog. I've got some things there that hopefully you will find interesting, like a statistics tip series, as well as posts showing that you are not alone if you're confused by statistics. I'll also be posting on the Facebook page, Statistics from A to Z, and on Twitter as @StatsA to Z.